Welcome to my channel, and today we look at the inclusion-exclusion principle. Now, so in today's topic, I'll suppose that A is a set of elements. Now, if A has k elements, I will denote this. We denote this by nk is 4. That means the number of elements in not nk, not just a minute. It's what did I say? If A, I said that if A has k elements, then I'll write that the number of elements in A are k. So that's what how I want to be writing the number of elements in a set. Now, e.g., if I have this set that has A, B, C, then I can see that the number of elements in B are 3. The number of elements in B are 3. So that's how I'll be denoting the number of elements in a set. Now let's look at one example for me to introduce the inclusion-exclusion principle. Let me look at some set A and some set B. So suppose that I have set A with the elements ABC, and I have some set B with the elements XYZ. Then how many elements are in the union? How many elements are in the union of A and B? How many elements are in the union of A and B? Now, so what is the union of A and B? The union of A and B, in fact, you know how to get the union. The union of A and B, these are all the elements in A and all the elements, or all the elements in B. All the elements in A or all the elements in B. So how many elements are these? 1, 2, 3, 4, 5, 6. These are 6 elements. Now, so what does the inclusion-exclusion principle say? The inclusion-exclusion principle says that the number of elements in this union is given by the number of elements in A plus the number of elements in B minus the number of elements in the intersection of A and B. So we subtract the number of elements in the intersection to avoid counting some elements twice, because we've already counted elements in A, we've already counted elements in B, so we don't need to count some elements twice. So this is the inclusion-exclusion principle. So we are including the elements in A, including the elements in B, but then excluding the elements in the intersection. So for this example, the elements in A are 3, the elements in B are 3, and you can see that the intersection of these two elements has 0. These two sets have 0 elements. So that means the elements in the union are 6. Let me just use another example. Let me erase this first of all and look at another example. You're still looking at the inclusion-exclusion principle. So let X be the set comprising of 1, 2, 4, 5, 8, and Y be the set comprising of the elements 4, 8, 10, 12. So the question is, find the elements in X union Y. Find the elements, the number of elements in the union. So let's look at the solution to this question. So the question is, find the number of elements in the union of X and Y. And I want to use the inclusion-exclusion principle. Inclusion-exclusion principle, which says that the number of elements in the union is the number of elements in X plus the number of elements in Y minus the number of elements in the intersection of X and Y. So the number of elements in X are 1, 2, 3, 4, 5. The number of elements in Y are 1, 2, 3, 4. The elements in the intersection, those are the elements common to the two sets. So I can see that this set has 4 and 8. This set has 4 and 8. So these are two elements. So what I'm saying is that the intersection of X and Y has two elements. The intersection of X and Y has two elements. The elements there are 4 and 8, 4 and 8. So those are the elements common to these two sets. So this one has two elements. So that means that the number of elements in the union therefore will be 9 minus 2, which is 7. So that is when you use the inclusion-exclusion principle. Now, you may have wanted to do it different without using this principle. You will have gotten the same result, because that means that if you don't want to use this method, then you first of all finding the union. You find the union of X and Y, and then counting the elements there. So the union here, it has 1, 2, 4, 5, 8, and then you don't repeat the elements. So I'll not repeat. So those are the elements in X, and then the elements in Y, we don't repeat 4 and 8 because it's already there. So we add there 10 and 12. So you can see that this union has 1, 2, 3, 4, 5, 6, 7. So therefore, the number of elements in the union are therefore 7. So if you did not want to use the inclusion-exclusion principle, then this is how you would have done it. Now, so what the inclusion, these are two sets. What the principle says is that we shall take the elements in X plus the elements in Y minus the elements in the intersection. That's what, so we are including the elements in X and then include the elements in Y, and then exclude the elements in the intersection. And this is done so as to avoid counting the elements twice, because you can see that 4 and 8 has been counted here and has also been counted here. So we remove it so that we just count 4 and 8 once. Now, so that is what the inclusion principle says for two sets. What about for three sets? So I want to look at three sets, and then we generalize to more sets, more than three sets. We see what the inclusion-exclusion principle says. Now, so if we have three sets, let me say, supposing we have sets A, B, and C, then the number of elements in the union of A, B, and C will be given by, we include the elements in A, include the elements in B, include the number of elements in C, and then exclude the elements in the intersection of A and B, exclude the elements in the intersection of A and C, exclude the elements in the intersection of B and C, and then include the elements in the intersection of A, B, and C. So this is what the inclusion-exclusion principle says for three sets. E.g., if X is a set comprising of 1, 2, 3, 4, and 5, B, let me say Y, is a set comprising of 2, 4, 6, and 7, and then Z, the set comprising of 5, 7, 9, then find the elements, the number of elements in X union Y union Z. Find the number of elements there. So what would be the solution? Our solution is, by the inclusion-exclusion principle, the number of elements in the union of X, Y, and Z will be given by the elements in X, the number of elements in X plus the number of elements in Y plus the number of elements in Z minus the number of elements in the intersection of X and Y minus the number of elements in the intersection of X and Z minus the number of elements in the intersection of Y and Z, then plus the number of elements in the intersection of X and Y and Z. So let me add one element in Z. Let me just add one element in Z. I want to add one element here. Let me just add an element 4 here. I want to add that element 4. Now, so this would be the number of elements in X are 1, 2, 3, 4, 5. The number of elements in Y are 1, 2, 3, 4. The number of elements in Z are 1, 2, 3, 4. The number of elements in the intersection of X and Y. So the elements common to X and Y is this 2, which is in X and is in Y. This 4 is in X and is in Y. And there is no other element. So how many elements are these? 1, 2. Those are 2 elements. What about in the elements in X and Z? X and Z, I can see this 4 in both. I can see this 5 in both. And any other element, 3 is not there, 1 is not there. So there are 2 elements again in the intersection of x and z. What about the intersection of y and z? The intersection of y and z, I can see 4. I can see 4 there. I can see 7 there. 2 is not in z. 6 is not in z. So I can see again that the intersection of y and z has 2 elements. What about the intersection of x, y, and z? Intersection of x, y, and z, I can see only one element, 4. 4 is in x, 4 is in y, 4 is in z. So it's in the intersection of these 3 sets. There's no other element because I can see that 1 is not in y, 2 is in y but is not in z, 3 is not in y, is not in z, 4 is the only element in the 3 sets, 5 is in x and is in z but is not in y. So the intersection of these 3 sets has one element. So we've included 5, 4, 4, excluded 2, 2, 2, and then included 1. So what is this? This is 9. 9 plus 4, that is 13. 13 minus, this is 6. That will give us 7. 7 plus 1, that will be 8. So that means the number of elements in the union of these 3 sets is 8. That is when we use the inclusion-exclusion principle. If you didn't want to do that, let's see if the other way would have given us the same answer. The other method of just finding the union, then counting the elements there. Let's see if we've gotten 8 as the answer. Let's see this other one. The union of x, y, and z has the elements in x are 1, 2, 3, 4, 5. So we write the elements in y, but we make sure we don't repeat an element. So we cannot write 2 because it has already been written. 4 we cannot write it because it has already been written. But 6 has not been written here. And 7 has not been written here. Okay, let's come to this z. Anyways, in z, 5 has already been written. 7 has already been written. So 9 is the one that has not been written. 4 has already been written. That means the union has this. So how many elements are these? 1, 2, 3, 4, 5, 6, 7, 8. That means the union of these elements has 8 elements. Now, so for this question, we can get the union and then count the elements. But there's other questions where you cannot find the union. And so that the only method that will work for those questions is the inclusion-exclusion principle. So then let's look at such examples where we cannot find the union, that it's only inclusion and exclusion principle that will work. Let's look at such examples. The example says Bank M has 314 customers. 314 customers. In a certain month, 101 of these customers took car loans. 90 took 90 customers took investment loans. And 72 customers took school fees loans. Of these customers who borrowed, of these customers who borrowed, 20 took both car and investment loans. 20 took both car and investment loans. 25 took both car and school fees loans. 25 took both car and school fees loans. Fifteen took both investment. 15 took both investment and school fees loans. Full stop. If 7 of these customers who borrowed, 7 of these customers who borrowed took all the 3 loans, but A, find the number of customers who took at least one of the loans. Find the number of customers who took at least one of the loans. B, you can write that question, you just write it. Find the number of customers who took at least one of the loans. B, how many customers never took any loan? So that is, find the number of customers who did not take any loan. You remember we had 314 customers. So the question is, how many of these 314 customers did not take any loan? So that is question B. Question C, draw a Venn diagram. Draw a Venn diagram to represent. Draw a Venn diagram to represent the above information. To represent the above information. And then is D, how many customers took only car loans, comma, only investment loan, and those who took only school fees loan? So that's the question that I want to answer. So I hope you've noted question A properly and question B properly and then question D properly and C, so that we now try to answer the questions. Now, so we'll use the inclusion-exclusion principle to do this. We have 3 sets. One, the set of the customers who took car loans. Then you have the set of customers who took investment loan. Then you have the set of the customers who took school fees loans. And those who took school fees loans was 72. Then we have those who took all the 2 loans each, and those who took all the 3 loans, and then those who did not take. So let's now answer the question. Let me get some space here for the answer. Now we've already said that we have 3 sets. Our sets are, we have those who took car loans, we have those who took investment loans, and we have those who took school fees loans. So the question is, how many people took all these 3 loans? So those who took, the number of people who took car loans, union investment loans, union school fees loans. So I'm answering question A. So the question is, question A was, find the number of customers who took at least one of the loans. Now, so this would be given by the number of those who took car loans, plus the number of those who took investment loans, plus the number of those who took school fees loans, minus the number of those who took car intersection I, minus those in car intersection F, minus those in F intersection I, plus those in the intersection of car I and F. So that is what the inclusion-exclusion principle says, that we shall include those who took car loans, include those who took investment loans, include those who took school fees loans, exclude those in the intersection of car and investment, exclude those in the intersection of car and school fees, exclude those in the intersection of school fees and investment, then include those in the intersection of C, I, and F. Now, so those who took car, the question says that they were 101. Those who took investment loans, the question says they were 90. And those who took school fees loans were 72. Those who took car and investment, the question says that of these customers who borrowed, 20 took both car and investment. 20 took both car and investment. And the question proceeds and says that 25 took both car and school fees. 25 took both car and school fees. And then what about fees and investment? The question says these ones were 15. Then the question says that 7 took all the 3 loans. That is what the question says. 7 customers took all the 3 loans. So when you do this question, you will find that the answer here is 12 and 10. So 210 customers took at least one loan. B, the question says, how many customers did not take any loan? So the number of customers who did not take any loan would be the original number of customers minus those who took loans. And so this will give us 104 customers. And then what about part C? Part C says draw a Venn diagram. So a Venn diagram is just a we must first of all in the Venn diagram we are relating these three sets. We have the set of those who took car loans. We have the set of those who took an investment loan. We have the set of those who took school fees loans. And then we must have a universal set represented by a rectangle. A universal set. So the set of all the customers represented by a rectangle. And then the other sets represented by these circles. Now, so let's begin by inserting those who took all the three loans in this intersection of the three loans. So 7 took all the three loans. Let's now insert those who took at least 2 loans each. So the question says, of those who borrowed, 20 took both car and investment. Car and investment is this intersection, and it represents 20. We already have 7 in this intersection. That means the remaining part is 13. Then the question says that we have this 25 who took both car and fees. Car and fees 25. But we already have 7 inside this 25, so that means we're left with 18. And then we have this 15 who took fees and investment. Fees and investment 15. So this intersection must be 15, but we already have 7 in it, so we are left with 8. So the question again says that 101 customers took car loans. So car loans is this circle. It must be 101. But we already have 18, 7 and 13 in it. So when you add 18, 7 and 13 and subtract from 1 or 1, then you discover that we have 63 who are left here. And then we also told 90 took investment. So the circle of investment is this, it must be 90, the total must be 90. The number of customers here must be 90. You already have 13 plus 7 plus 8 inside this circle. So that means we are left with 62. When you add 13 plus 7 plus 8 and subtract from 90, what you get here is 62. Then the question says 70 took fees. So this circle that represents school fees must have a total of 70. But we already have 18 plus 7 plus 8. So when we add this and subtract from 70, not 72, when we subtract from 72, we get that 9 is left here. Now, so these are the customers who took loans. 63 plus 62 plus 13 plus 7 plus 18 plus 8 plus 39. These are the customers who took loans. So when we add this and subtract from 314, we get those who did not take loans. And we can write them here. 104. These are the customers who did not take loans. So the question proceeds and says that how many customers took only car? So those who took only car will be 63. This one, 63. You see car, those who took car were car and something else. The total number of those who took car loans were 101. But of this 101, some of them took car loan and something else. So those who did not take something else, they only took car loans, were 63. And those who only took investment loans were 62. And those who only took school fees loans were 39. So these are the customers who just went and said, I just want school fees loans only, and left the bank. Those ones were 39. Those who went and said, I just want investment loan alone, they were 62. And those who said, I just want car loan alone, they were 63. So this is how you answer this type of question. And you've seen that we've used the inclusion-exclusion principle. Now, so we want to look at more other examples. Now, let's look at other examples. Let me clear this space so that we can use it for two other examples. Just clear the whole thing. No, just clear the working so that the topic remains. Now, I want us to look at two easy examples that will help us understand the knowledge of the inclusion-exclusion principle. Now, the first example, extra example that I want us to look at is that find positive numbers. Find positive numbers less n, which is less or equal to 15, that are not divisible by 2 or 3. So want positive numbers which are not divisible by 2 or 3, and this number should be less than or equal to 15. Now, so somebody else would have done this by listing the numbers between 1 and 15. Somebody else would have done that. Let's just see. But I'll use another method, the one of inclusion-exclusion. But let me just see, if it's a small number like 15, somebody else can easily list them and count the numbers which are not divisible by 2 or 3. And you can see that one of the numbers is 1, the other number is 5, the other number is 7, the other number is 11, the other one is 13. So these are the numbers which are not divisible by 2 and they're also not divisible by 3. So how many are they? 1, 2, 3, 4, 5 numbers. So one could say the answer is 5, and look at how this person has done by listing the elements and then counting those which are not divisible by 2 or 3. But this would be time consuming if you are given a bigger value here. If n was bigger, supposing n was 1,000, you cannot list all the digits between 1 and 1,000 and then count those which are not divisible by 2. That will take a lot of time. You can do it, but it will take a lot of time. But let me see, what is the easiest way of doing this? So the easiest way of doing this is to use the inclusion-exclusion principle, and let's first of all find the number of elements which are divisible by 2 and 3, and then we subtract from 15. So let n1 be the set of elements, let it be the set of elements less than or equal to 15, which are, just a minute, let me write it properly. Let it be, just a minute, let this be the natural numbers. That means it numbers from 1 and so on. Let this be the natural numbers which are less than or equal to 15, and 2 divides them. Let n2 be the other set of natural numbers which are less than 15 or equal to 15 and are divisible by 3. They are divisible by 3. So how many numbers are these? So n1, how many numbers are these? How many numbers between 1 and 15 are divisible by divisible by 2. So the numbers between that which are divisible by 2 would be 7. So I just took 15 divided by 2. I found that there will be 7 numbers which are divisible by 2. In fact, you can try and see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Count those which are divisible by 2. 1, 2, 3, 4, 5, 6, 7. So we found that the number of elements divisible by 2 are 7. What about the number of elements divisible by 3? The number of elements divisible by 3, so if I take 15 divided by 3, just 5. So then 5 elements divisible by 3. In fact, you can just count the number of elements divisible by 3. 1, 2, 3, 4, 5. Those are the number of elements divisible by 3. And you can see how I did that. Very easy. I just took 15 divided by 2 to get the number of elements divisible by 2. And then took 15 divided by 3 to get the number of elements divisible by 3. So what does the inclusion-exclusion principle say? It says that the number of elements which are divisible by both these two numbers, 2 and 3, would be the number of elements in N1 plus the number of elements in N2 minus the number of elements in the intersection. So what I wanted to add here, I should have added the number of elements in the intersection therefore. I want to show you how to do that. The intersection of 2 and 3, the number of elements, I just multiply 2 and 3 and I get 6. 6 divided into 15. And 6 would go there 2 times. So the number of elements which are divisible by both 2 and 3 are 2. And you can see which ones are these? Which ones are these? 3 is not, 4 is not, 6. 6 is one of them. Is it divisible by both 2 and 3? 9, 15, 12. 12 is another one. 12 is another one. Is it divisible by both 2 and 3? So there are only 2 numbers. And therefore, this result, therefore, would be the number of elements divisible by 2 was 7. Those divisible by 3 were 5. And those in the intersection, those divisible by both 2 numbers, those 2 numbers would be 2. So when I add this, I would get, this is 12. This gives me 10. This is 12 minus, that is 10. So these are the number of elements divisible by both of these numbers. Divisible by 2 or 3. These are the number of elements divisible by 2 or 3. And you can count. You can count. This is divisible by 2, so that's 1. Divisible by 3, that's 2. Divisible by 2, 3. This one 4. This one 5. This one 6. This one 7. This one 8. This one 9. This one 10. So those are which are divisible by both, by either 2 or 3. Their total number is 10. So what does the question want? The question wants the number of elements not divisible by 2 or 3. So the required answer is 15 minus 10, which is 5. And that's what we have gotten earlier when we started. But now we've used the inclusion-exclusion principle. Now we can generalize this inclusion-exclusion principle to more than 2 sets, more than 3 sets, and so on. let me look at an example that includes more than 2 sets. And that is the last example for today. Now, so let's write the question. The question says, find the number of integers. Find the number of integers between 1 and 1,000 included, which are not divisible by by 2 or 3 or 5 or 7, which are not divisible by any of these numbers. Now, so you can see this 1,000 is a very big number, so you cannot list all the numbers and then start counting those which are not divisible by any of these. So that means that our inclusion-exclusion principle comes in very handy. So let's let n1, n2 be the set of those which are divisible by 2, n3 be the set of those which are divisible by 3, n5 be the set of those which are divisible by 5, and n7 be the set of those which are divisible by 7. So by inclusion-exclusion principle, we have that the number of elements in this union will be given by the number of elements in N2 include those in N3, include those in N5, include those in N7, exclude those N2, N3, exclude N2, N5, exclude N2, N7, exclude N3, N5, exclude those in N3 intersection N7, exclude those in N5, N7, and then include those in N2, N3, N5, include those in N2, N3, N7, include those in N2, N5, N7, include those in N3, N5, N7. I think I've included everything there, and then I now want to exclude those in N2, N3, N5, N7. So remember, we're excluding to ensure that there is no counting elements twice. How many are these? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. See, that is okay. So many? 15 is okay. that is what the formula says. Now, so what is that? So the question is, the answer is, so this will give us the number of elements that are divisible by all these, by divisible by 2, plus those divisible by 3, plus those divisible by 5, plus those divisible by 7. If you do this, you get all those. Then we subtract that from 1,000 to get those which are not divisible. So those divisible by 2, the question has told us, okay, so just 1,000 divided by 2, that will be 500. And then 1,000 divided by 3, that will be 330. I think, no, 333. 333. And then 1,000 divided by 5, that will be 200. Then 1,000 divided by 7, that would be 142. Then minus, so we are done up to here. This is 2 times 3, which is 6. 6 divided into 1,000, that gives us 166. And then this is 2 and 5, that is 10. Divided into 1,000, that would be 100. We are done with that. And then we are here, 14 divided into 100. No, not 100, it's 1,000 actually. Why am I saying 100? It's supposed to be 1,000. In all these questions, it's 1,000. So that is 14 into 1,000, that will be, use your calculator and get 71. And then this is 15. 3 times that, that's 15 into 1,000. Use your calculator and get 66. We are here, that's 21. 3 times that's 21 into 1,000. What do you get? Use your calculator and you get 47. That is, this is 35 divided into 1,000, and you get 28. And let's come here. This is 30. This is 30 divided into 1,000. That gives you 33. I'm only taking the whole numbers actually. The decimals, ignore them. And this is 6 times that. That is 42. Divided into 1,000, you get 23. And this other one is 1070. Divided into 1,000, you get 14. This other one is this is 15 times that. That looks like 105. 105. Just multiply. That is 105. Divide that into 1,000, and you get 9. Then what about this? 2 times 3 times 5 times that. That result divided into 1,000, you get 4. So when you do this, what you get is 772. So 772, these are the numbers which are divisible by 2, plus those which are divisible by 3, plus those which are divisible by 5, plus those which are divisible by 7. So the question is, how many are not divisible by n of this? So those which are not divisible by n of this is the required answer, and that is given by 1,000 minus 772. and this gives you 228 numbers. These are the numbers which cannot be divided by any of these. And that is how we use the inclusion-exclusion principle. You may want to look at more at examples so that you are very well versed with this topic.